Human language is chaotic and ambiguous, while computers demand rigid mathematics. Natural language processing bridges this exact gap. Modern systems bridge this divide using a precise six-stage evolutionary engineering stack. This progression starts with basic text cleaning and rudimentary probability, building toward the parallelized transformer architectures that power modern artificial intelligence. To understand this system, we have to recognize that every major breakthrough was a new method for manipulating high-dimensional geometry and probability. Raw linguistic data is noisy. Before a machine can interpret a sentence, it must be split into computable, discrete units through tokenization. Developers then standardize these tokens. They either use stemming to chop off suffixes based on heuristic rules, or lemonization to trace a word back to its exact dictionary root. With the words isolated, algorithms apply part-of-speech tagging and named entity recognition to identify nouns, verbs, and proper entities. The challenge is representing these tokens mathematically. Early methods like one-hot encoding or bag of words created extreme sparsity, producing massive arrays of zeros that failed to capture the context between terms. This is the TF-IDF formula. It represents the statistical apex of discrete representation by weighting specific topical terms against generic vocabulary. The function penalizes common words that appear across an entire corpus, while boosting the mathematical weight of rare, context-specific vocabulary. While TF-IDF is effective for categorizing documents, it ignores word order and fails to capture semantic relationships between words. In 2013, Word2Vec solved this by embedding words into dense, continuous distributed representations within a lower dimensional space. In the continuous bag of words architecture, the model takes surrounding context words as inputs to predict a missing target word. The skitgram architecture reverses this. It uses one target word to predict the probabilities of the surrounding context. Subsequent models like FastText improved on this by embedding character n-grams instead of whole words, allowing the system to construct vectors for misspelled or new vocabulary. With text converted into continuous vectors, classic machine learning algorithms could process the data. Naive Bayes used conditional probability to classify text based on the frequencies of these embedded features. For more complex classifications, support vector machines calculated the optimal hyperplane to separate high-dimensional textual data into distinct categories. Continuous vectors gave machines a geometric understanding of synonyms, but traditional algorithms still struggled to process complex sequential word order. Engineers initially tackled sequence labeling using generative models like hidden Markov models, before advancing to discriminative approaches like conditional random fields. The shift to deep learning introduced recurrent neural networks, which process temporal sequences by passing a hidden state from one word to the next. Standard RNNs face the vanishing gradient problem. As signals pass through the chain, they mathematically fade toward zero before the sentence ends, causing the model to lose the memory of early words. The architectural solution is the long short-term memory network, or LSTM. It introduces a continuous cell state track that runs across the entire sequence. Inside each cell, a forget gate uses a sigmoid function to determine which information is mathematically dropped from that central memory track. Simultaneously, input and output gates calculate which new information is integrated into the cell and which values are passed forward as the next hidden state. For deployments on devices with limited hardware, engineers use the GRU architecture, which merges these gates to reduce the VRAM required for computation. LSTMs successfully solved sequential memory, but their word-by-word processing requirement limited training speed on internet-scale datasets. In 2017, the industry abandoned recurrence for an architecture that processes every word in a document simultaneously, enabling massive parallel computation. This breakthrough centers on the self-attention mechanism. Self-attention relies on three learned weight matrices. The query matrix represents the current words searching for relevant context. The query performs a dot product multiplication with the key matrix, which acts as an identity tag for all other words to evaluate their relevance. The final component is the value matrix, which holds the actual semantic meaning of the words. The scaled dot product attention formula calculates the final weighted output vector by determining how much of the value matrix to integrate based on query and key scores. To stabilize gradients during training, the scores are scaled by the square root of the dimensions and passed through a softmax function. Transformers use multi-head attention to calculate grammatical, entity, and contextual relationships in parallel. Encoders, like BERT, analyze entire documents to build bidirectional context, while decoders, like GPT, use masked attention to optimize for sequential generation. By decoupling context from linear time, the transformer allowed artificial intelligence to train on the entire internet, launching the era of large language models. Through massive pre-training on next word prediction, these models develop comprehensive logic and general reasoning capabilities. This enables few-shot learning, where a model performs novel tasks using only a few examples in its prompt, without internal weight updates. However, fine-tuning a billion-parameter model for specific tasks requires specialized, expensive GPU clusters. LoRA, or low-rank adaptation, bypasses this hardware requirement by freezing the massive primary weights and training only two tiny low-rank matrices. This method reduces the memory load from gigabytes to megabytes by only updating the values inside these smaller matrices during training. QLoRA compounds this by quantizing the base model to 4-bit precision, allowing 70 billion parameter models to fit on consumer graphics cards. To reduce hallucinations, engineers use retrieval-augmented generation, connecting the LLM to external vector databases to ground its answers in factual evidence. Modern NLP relies on this pattern, freezing massive general intelligence and dynamically patching it with task-specific adaptations and retrieved context. This evolution defines the current software stack. Engineers use Spacy for rapid preprocessing and Genzim for spatial representations. They deploy transformer weights from Hugging Face and use LangChain to orchestrate RAG pipelines and system memory. The focus has now shifted toward agentic AI, autonomous systems that plan multi-step processes, browse the web, and execute code. Today, text, vision, and audio are all mathematically mapped into the exact same continuous high-dimensional vector space. Whether building a statistical spam filter or an autonomous multimodal agent, the engineering remains rooted in high-dimensional geometry and probability.